Hello, everyone. Last session of the day, and you'll be glad to hear that this is quite a short presentation without much mathematics. So I am Sharath, and I am a PhD student in a joint program between NTU in Singapore and the University Grenoble Alpes in Grenoble, France. And today I want to discuss some work about real-time pricing using offline reinforcement learning. Can I use this one? Oh, okay. Okay. To quickly motivate my work, I can build on the talks that we have listened so far across many sessions, but I would start with addressing the problem that I'm interested in, which is demand response. And the first thing is that the available flexibility from demand response today is not sufficient to cover our net zero goals, according to the IEA, and it has to increase by a lot in the next 10 years. And in this context, there is interest in incorporating more players into the demand response scenario. So I'm interested in the problem of residential demand response using residential households and how can we get them to participate. But in the literature, there have been many approaches proposed and a lot of benefits have been quantified in this field. But in the real world, it has been found that it's very difficult to achieve residential demand response, mainly due to many social and technological challenges associated in this. So I seek to address one specific challenge, which is that there is a lack of works which consider the problem of how to generate real-time electricity prices, which can encourage a set of residential consumers to behave in a certain way. So in a sense, if I will describe my use case. So I have a group of 100 consumers who have decided to participate in a personalized real-time pricing scheme in which every person in the scheme gets their individual price for every time slot in the day. And the question is, yes, these consumers are residential consumers who are strictly providing flexibility by load shifting. So they are not doing curtailment, they are shifting loads. And it is assumed that they have some automated system in their house to do these response to prices. And the question is, how can you generate the prices that give you the benefits that you want from the perspective of the aggregator? So in short, the idea is to use a reinforcement learning agent, which is trained offline and deployed across this group of buildings to do this job. So with this in mind, the key contributions that I seek to give with this paper, one is the consumer model itself. While there is plenty of literature on studying price elasticity-based consumer models, there is some novelty in the model itself that I will present in the subsequent slides. The more important one is the mechanics of the real-time pricing scheme itself, in which there is a constraint which we incorporate to try and ensure an element of fairness in the prices. And finally, the other important thing is that the entire scheme relies only on smart meter measurements to make its pricing choices. So let's get started with the overview of the problem. So as we can see here, there is a service provider who aggregates the electricity demand for a group of consumers. And the service provider's job is to provide a real-time electricity price for every consumer at every time slot. The inputs, as we can see, they are smart meter readings, and the service provider wants to generate the prices which can be used to maximize its own profit while reducing the grid peak to average ratio, and that's the idea. Now, one novelty of the proposed approach is this constraint on the prices themselves. So the idea is that in the contract, there exists a constant value, pi b, which is constrained to be the average price over the day for every consumer. So for every consumer, at the end of the day, the average price over the day must be equal to this value. This is the constraint. And as we will see, this provides some interesting perspectives on fairness of the finally generated prices. Now, the consumer model itself, it's quite simple. What it is doing is I have a load shifting model of a consumer, but the daily consumption is a fixed value. It's just that the consumer has the ability to shift the load in response to the prices. And the inputs here are some load profiles which the consumer wants to have through the day. This is hidden information from the perspective of the aggregator. There are some price response parameters and the price signals. And the model outputs the final consumption after acting on the prices. So just for demonstration purposes, here are some of the things that the model captures. So for example, as we can see in real world tests, this model captures things like rebound peaks, which occur when you have a peak to off peak transition in the price. And what the consumer essentially does in the low prices period is that they try to shift consumption from future planned high peaks into this period. And when they see higher prices, they seek to delay their consumption. And that magnitude of the shifting is parameterized by a parameter epsilon. So now to come to the price generation strategy itself, which is the main idea in the paper, I propose an offline reinforcement learning approach, which is training a reinforcement learning agent to solve this problem using a simulated environment based on historical observations of the demand. So the way this works is that, of course, there is a very big important assumption here, which is that the aggregator has a very good idea, very good knowledge about the parameters which govern the response of individual consumers to prices. So they don't know the actual future demand itself, but they know what the reaction to the prices might be. Under this context, what we can do is we can create synthetic a synthetic environment in which a reinforcement learner can learn to solve the problem of generating prices in order to maximize some objective value. So the important thing is that in this formulation, we can have an architecture in which the inputs to the reinforcement learning agent are all things that you can measure at time t. So there are no forecasts involved at all. And the reinforcement learner's task is to learn the policy which maps from real-time measurements of the various variables to a price value for each consumer, with the objective of maximizing its profit while respecting the earlier mentioned constraint. So this is the architecture, and the way it works is in 3 steps. So we propose a scheme where every group of consumers, when I say group, I mean a group consisting of consumers with similar consumption. For each one, there is a dedicated agent that seeks to generate prices for all consumers in that one group. So this is the idea. And since it's a short presentation, I quickly go to the results. So here are some of the results that we were able to observe from this sort of training idea. And I would like to highlight 3 major points from this. The first thing is that we are able to achieve, or we can see that based on the consumer model described earlier, these kinds of prices, which vary across consumers and across time over the day, can achieve peak shaving by getting a more distributed aggregate load curve. But if we can compare it against a typical demand response pricing scheme, such as a time of use scheme, we see that the same model predicts a load shifting action, which often is not something that we want. So the second one is that there are economic benefits and grid benefits when using these kinds of prices. We notice a 12% reduction in the peak to average ratio and a 7% increase in the profit without an increase in consumer bills. So this 7% profit increase, of course, it would have to be distributed back to the consumers in some scheme. But the fact is that there is an economic incentive which can reduce the consumer's bills while still increasing the aggregator's profit. And finally, we also see that these prices, which vary over the day, still manage to satisfy the constraint. And what you will notice here is that by virtue of having such a constraint, for every consumer, if they see a period where there is a high price, it ensures that it will be offset in the future by a period of low price. So this ensures that with the sort of control scheme at the consumer side, it is possible for them to optimize their consumption and shift it to some period where the prices are low. So that is the idea behind the notion of fairness that I present here, which we argue can be done through this kind of constraint. And so to conclude, the main contributions from this work are that we have a real-time price generation scheme, which is something that is not well addressed in the literature, especially when you only use smart meter data to make the prices. The second one is that the scheme, because of the clustering-based approach, can scale to a large number of consumers. And we incorporate aspects of price fairness through the constraint and also consumer privacy, because we don't use much data to make the prices. And we also quantify the benefits based on models. But before I conclude, I would like to, of course, acknowledge certain limitations of this work. And the main one, of course, is this assumption that we know the consumer parameters, which might not exactly be realistic. Then, of course, there are model-related aspects, such as if you include curtailment, how that changes things. And also, to be able to get a fair assessment, we also need to explicitly simulate the flexibility source. Underlying flexibility source might be an HVAC system with a thermal model, etc. Right now, it's a numerical load shifting model of the consumer. So yeah, these are some things that I would definitely like to acknowledge. And I hope the presentation was clear, and I would like to take some questions now.